So here's a couple of identities. You might be asked to prove similar problems. Verify the identity sine squared of 2 alpha divided by sine of alpha equals 4 minus sine squared of alpha. And so the first thing to do is replace our formula for sine of 2 alpha with 2 sine alpha cosine alpha, and since this is squared, we would have to square that. And squaring the 2, we get a 4. Squaring the sine of alpha, we get sine squared of alpha. Squaring the cosine of alpha, we get cosine squared alpha. Now I think you can see easily that the sine squared alpha and this sine squared alpha will cancel. So we get this side equal to 4 cosine squared alpha, and then we would replace the cosine squared alpha with 1 minus sine squared alpha, which leads us directly to what we're trying to prove. So that was a fairly easy one. I won't say these are all easy, as you'll see here in a little bit. Here's another one. Verify the identity tangent t plus cotangent t equals 2 cosecant 2t. You might pause for a second to see how do you think you would start that one out. If you can get past the starting point, I think the rest is fairly easy, although it does have one little sneaky twist in it, at least the way I did it. I worked with the right-hand side. Resuming from your pause, I think I would do this. I would say, well, let's replace this cosecant of 2t with 1 over sine of 2t. And so that means we would have 2 divided by sine of 2t, which is 2 divided by 2 sine t cosine t from our double angle formula. And so that means what we would really have is 1 divided by sine t cosine t. And that looks like a stopping point. Like, wow, I'm stumped now. What could we do from here? And this is a nice little trick. Sometimes you can replace 1 with a convenient Pythagorean identity. For example, 1 is equal to secant squared minus tangent squared, but I don't see where that one would be very helpful. However, 1 is also equal to sine squared t plus cosine squared t, and I do see where that one might be helpful. Notice replacing this 1 with sine squared t plus cosine squared t. Now, separating this into 2 separate fractions, one of them would be sine squared t over sine t cosine t, the other one cosine squared t over sine t cosine t. And notice that one of the sines cancels out from these, and one of the cosines cancels out from this fraction, leaving us with sine t over cosine t plus cosine t over sine t, which is another way of saying this one's tangent t, this one's cotangent t, which is what we set out to prove in the first place. Here's a hard problem. Try to solve over the interval 0 to 2 pi cosine 2 theta minus tangent theta equals 1. And I'll say pause here to give you a chance to at least start it out. Resuming from the pause, I would hope you would see that since we are talking of the double angle formulas, that might be a good plan. Do something with that first. So I replace cosine 2 theta with cosine squared theta minus sine squared theta. I replace tangent theta with sine theta over cosine theta. Now the problem with this is I have still 2 different trig functions mixed up in there, sine and cosine, so it's going to be hard to work with it algebraically. However, one thing I could do is multiply both sides of the equation by cosine theta, giving me cosine cubed here, cosine times sine squared theta here, sine theta here, and just cosine theta on the right-hand side. Again, we do have the problem that we've got 2 different trig functions. One thing we could easily do is replace this sine squared with 1 minus cosine squared. And I'm going to subtract this cosine theta from both sides and add this sine of theta to both sides here eventually. And you could see that then from this algebraic thing that we got this cosine cubed and this minus a negative, so plus this cosine cubed, so 2 times cosine cubed. We have this minus cosine theta, and this one on the other side would be a negative, so minus cosine theta equal to this sine of theta. Now, this still is a problem because we don't have one side 0 and we got 2 different trig functions mixed up in this. So what's the plan here? The plan here is we can always replace sine with something in terms of cosine, although it will have a radical. And the answer is this would be actually plus or minus square root of 1 minus cosine squared. That's our replacement for sine theta. This side I just factored out the cosine theta and the 2. I had the 2 factored out already, but factored out an extra cosine theta. Because I'm about to square both sides, so I could search out a plus or minus for this and paste that in there, but I'm going to square both sides anyway, so that's going to take care of that issue. Squaring the left, we'd square the 2, 4. Square this, cosine squared. Square cosine squared theta minus 1, we get cosine to the 4th theta, minus 2 cosine squared theta plus 1. Squaring this radical, we just drop the radical. So now we finally got what we wanted. Everything is in terms of cosine theta. However, we do have a pretty nasty polynomial equation in cosine theta. Let's see if we can simplify it. We got 4 cosine to the 6th theta minus 8 cosine to the 4th theta plus this 4 cosine squared theta and this 1 cosine theta, so 5 cosine squared theta, and then plus 1. This 1 is actually times 4 cosine squared theta, so good gracious, here's what we have. Simplifying that, we've got this. Trust me on that one. Work it out yourself in great detail. But that's a complicated looking polynomial in terms of cosine to the 6th theta. So let's simplify it a little bit. Let's let x be cosine squared theta. That might not be something you would dream up on your own, but notice it's only even power, so we could at least simplify it in that way. And let me just say, if x equals cosine squared theta, then here's what we really need to solve. This cubic polynomial equation, 4x cubed minus 8x squared plus 5x minus 1 equals 0. In chapter 4, or somewhere along your mathematical careers, if you didn't use our book for chapter 4, when you were solving polynomial equations, you had something called the rational root theorem that says all possible rational roots, the numerator will divide the negative 1 and the denominator will divide the 4. So these are our possible rational roots for this one. X would be 1, negative 1, 1 half, negative a half, 1/4, or negative 1/4. So I made the determination by putting 1 in for x, so that would be 4 minus 8 plus 5 minus 1. Darned if that doesn't equal 0, so I know that 1 was a rational root. Then, when I divided x minus 1 into this polynomial, it turned out that I got the polynomial 4x squared minus 4 plus 1 as the quotient. So the whole thing factored as x minus 1 times 2x minus 1 squared. That quantity squared equal to 0. So I got two solutions, x equals 1 or x equals a half. A half is a double root. So remember, x was cosine squared theta, so cosine squared theta equals 1, or else cosine squared theta equals 1 half. Where are we going to go with that? Well, if cosine squared theta equals 1, then cosine theta equals 1, or else cosine theta equals negative 1. If cosine squared theta equals a half, then cosine theta equals 1 over the square root of 2, or cosine theta equals negative 1 over the square root of 2. Now I think we're ready to start thinking about our solutions. So cosine theta equals 1, that means theta is 0. Cosine theta is negative 1, means theta is pi. Cosine theta equals 1 over the square root of 2, two answers. Pi over 4 and 7 pi over 4. See the angle, reference angles, it's a 45, 45, 90 triangle. The reference angles where x is positive are pi over 4 and 7 pi over 4. Now, cosine theta equals negative 1 over the square root of 2. That would put us in quadrant 2 and quadrant 3, so 3 pi over 4 and 5 pi over 4. Now, is this the solution? I want you to pause and think about it. Zooming from the pause. In fact, that was too many solutions. The problem is, we squared both sides to get from here to here. And whenever you square both sides, you might be introducing extraneous solutions. That's solutions for the new equation, not solutions for the original. So here's the original equation again. Cosine 2 theta minus tangent theta equals 1. And notice that if we tried 0, it does work, because cosine of 0 is 1. 1 minus tangent of 0 is 0, so that works. And if you try pi, cosine of 2 pi is also 1. Tangent of 2 pi is also 0, so that one works. However, if we try pi over 4, cosine of 2 times pi over 4 is cosine of pi over 2, and that's 0. Tangent of pi over 4 is 1, so we'd have 0 minus 1 equals 1. That's not possible. 3 pi over 4 works, because we'd have 0 minus negative 1. And that does equal 1. 5 pi over 4 doesn't work, because tangent of 5 pi over 4, since it's in the third quadrant, is positive 1, we would have 0 minus 1, which is not 1. By the way, this would be cosine of 5 pi over 2 then, and if theta was 5 pi over 4. Cosine of 5 pi over 2 is the same as cosine of pi over 2, and that's 0. Think about what the x-coordinate is on the unit circle at pi over 2. And finally, it does work also for 7 pi over 4, because this would be cosine of 14 pi over 4, if you want to look at it that way, to make it 7 pi over 2, which is coterminal with 3 pi over 2. And cosine at 3 pi over 2, or negative pi over 2, is 0. The x-coordinate there is 0. So that would be 0, but it would be 0 minus negative 1, because the tangent is negative in the fourth quadrant where this angle is. And so that would be negative of negative 1, which is 1. So this is the actual solution to that particular problem.